All right, in this last section on number theory, we're going to talk about what happens when you have integers in other bases. So we're used to dealing in base 10, mainly because we have 10 fingers, 10 toes. So let's just talk about what that means. To be in base 10, going back to elementary school, you know you had a ones place, a tens place, hundreds place, thousands place. Then you learned about exponents, and we could talk about them as 10 to the 3, 10 to the 2, 10 to the 1, and 10 to the 0. So a number like 1,256 base 10 is 1 times 10 to the third, 2 times 10 to the second, 5 times 10 to the 1, and 6 times 10 to the 0. So that's kind of how we set up numbers, and notice that those are all tens because we're dealing in base 10. So if I wanted to convert this to some other base, let's say 5, that means that there's only going to be 5 different symbols or digits in that system. So 0, 1, 2, 3, and 4. Those are the only 5 we're going to use. So it's going to be something times 5 to the n, highest exponent of 5 that you want to go, and then 5 to the n minus 1, all the way down to something times 5 to the 0. Okay, and as I said, all of those are going to be digits between 0 and 4. So the question is, how do I create this number? How do I find out what this number is? Well, it's a very simple task, really. All you do is you just keep repeatedly dividing by 5 in this case, and keep track of the quotient and remainder. And then you keep going until you get a quotient of 0. Okay? And then once you have all of those remainders, you just read those remainders up, and that's your answer. So let's use a number like 1,256. And when we divide that by 5, we get 251 with a remainder of 1. And when I divide that by 5, I get a remainder, or I get 50 with another remainder of 1. When I divide that by 5, I get 10 with a remainder of 0. And when I divide that by 5, I get 2 with a remainder of 0. And when I divide that by 5, I get 0 with a remainder of 2. So now that I've got my quotient of 0, all I need to do is look at my remainders going up. And notice how they're all between 0 and 4, just like I said. So here's how I write it. I write the base as a little subscript after the number, so that way I know what base I'm dealing with. So 1,256 base 10 is the same thing as 20,011 base 5. All right, and you can check this. Remember, we said that this was some number to the highest exponent of 5, and then you keep going down by exponents of 5. So this would be 2 times 5 to the 4, 0 times 5 to the 3, 0 times 5 to the 2, 1 times 5 to the 1, and 1 times 5 to the 0. So 2 times 5 to the 4 is 1250. That's 0, that's 0. This is 5, and this is 1, and the whole thing does add up to 1256, which is the number that I started with. Okay, so it does work out, going back and forth. Now, what if you had a base that was greater than 10? We only have 10 digits to work with. And an excellent example of that is something that's used in computer science all the time, and that's something that's base 16, hexadecimal. So here's how they handle any system that has remainders between 0 and 15. Obviously, you can't use 2 digits to represent a single digit. So what they do is anything that was higher than 9, they replaced with a letter of the alphabet. So a remainder of 10 will be represented by the letter A, 11 is B, 12 is C, and so on, and then 15 is represented by the letter F. And you've probably seen these numbers that have the letters A, B, C, D, E, F, and in them along with the other 10 digits, particularly when you're doing something in computer science, like picking out colors based on a 6-digit code. So what we're going to do is we're going to look at the number 49,374, and we're going to see what that's worth base 16. So I'm going to go through the same process, divide by 16 until I get a quotient of 0. So when I divide this by 16, I get 3,085 with a remainder of 14, and remember 14 is represented by the letter E. Then if I divide that by 16, I get 192 with a remainder of 13, and remember that's represented by the letter D. If I divide 192 by 16, I get 12 with no remainder, so there's a remainder of 0 there. And then if I divide that by 16, I get 0 with a remainder of 12, and remember 12 is represented by the letter C. So if I read that up, I've got C, 0, D, E. And that spells code, kind of a cute little thing that I made up for you. And if you check that, take C, which is 12, multiply it by 16 to the third, take 0, multiply it by 16 squared, take D, which is 13, and multiply it by 16 to the 1, and take E, which is 14, and multiply it by 16 to the 0, and all of that adds up to 49,374, which is the number that I started with. Okay, so that's just converting back and forth between bases that are bigger than 10. Okay, now let's talk about addition. We're going to have to go back to old school, just like we did before. If I ever added a column of numbers and the sum was bigger than 9, what I would do is I would write the units number at the bottom, and I would carry any extra tens up to the top. Okay, well, same thing applies, but anytime I get a sum that is bigger than 1 minus the base, I'm going to carry any extra n's up to the next column as a 1 or more. All right, so let's do some examples here. All right, the first one is in base 7, so that means anything that is higher than a 6, I'm going to have to carry a unit or a digit up to the next column. So 6 plus 2 is 8, but in base 7, that is a 7 and a 1. So I've got a 1 down here, and then I've got an extra 7 up here, which base 7 would be represented by 10. So now I've got 1 plus 1 plus 3. That is 5. I've got 4 plus 1, that's 5. And I've got 6 plus 1, that's 7. But remember, 7 base 7 is 10. All right, now looking at multiplication. And I'm dealing in base 4. Okay, 2 times 1 is 2. And let me just get rid of this. 2 times 2 is 4, but remember 4 base 4 is 10. All right. 2 times 2 is 4 again, plus 1 more is 11. 3 times 1 is 3. 3 times 2 is 6, but 6 base 4 is a 4 and a 2, so that would be like 12. Okay. And then 3 times 2 again is 6, which is like 12, plus 1 is 13. And then we add all that up. 2, 0 and 3 is 3. 1 and 2 is 3. 1 and 3 is 4, but 4 base 4 is 10. And then 1 and 1 is 2. So 221 base 4 times 32 base 4 is 20,332. All right, so now let's look at divisibility in different bases. Kind of an easier concept, but we have to think of everything in base 10 first. If a number base n ends in 0, that means that it is divisible by n. So if we were dealing in base 10, if a number ends in 0, you know it's divisible by 10. Okay. Same thing with any base, though, if it ends in 0. So, for example, if I had 534,410 base 6, that ends in a 0, so it's going to be divisible by 6. Also, if you add up the digits of a number and you get a number that is divisible by 1 less than the base, then the original number is divisible by less than the base. We can prove that using modular arithmetic, which we talked about before. But let's just look at an example here. If I look at 52,413 base 6, those digits add up to 15, and 15 is divisible by 5, which is 1 less than the base. So the original number is divisible by 5. Okay, so just a couple of divisibility rules to remember when we're talking about numbers in different bases. Those kind of questions will come up. We'll talk about more of them tomorrow, and if you have any questions, please let me know.